Okay, welcome to this afternoon session. Let's get started. And our first speaker for this Thursday afternoon is Timoteo Carletti. He's a professor at Namur University, and he's going to tell us about Turing patterns from network to higher order structures.
Thank you very much. Good afternoon, everybody. Thank you for the organizer for this overflow conference. It's very interesting. And thank you for the invitation. It's a challenge for me to speak about Turing patterns here at the Alan Turing Institute. I'll to do my best. And so first of all, if you want, you have half of my email here. I think on the other screen you have the full one. So if you want, drop a mail. Otherwise, I will be there up to next Wednesday. So if you want to discuss with me, I will be available all the days. And so I have then to also acknowledge the student of mine, PhD postdocs and collaborators, especially Malbo Aslani in Florida State, Duccio from University of Florence, and of course Ginestra, that are the person with whom I have the most interesting new result about Turing pattern on networks and higher order structure. So the starting point of my talk is the observation that if you look around us, the nature has a lot of beautiful shapes that in some sense they spontaneously emerge. So you have this idea of that order, so all these shapes emerge spontaneously from the disorder. Why disorder? Because if you think of this cauliflower, there are a lot of billions of cells inside, but in some sense, they interact in some nonlinear way. But in some sense, they are able to produce this regular, having this fractal shape, or it can be on the skin of the fish, on the shells, on some chemical reaction. So the idea is try to understand which can be one of the underlying model or model that is able to reproduce this kind of behavior. And so today I will be interested more in the part which is the spot and stripes on the coat of animals. And I took this newspaper by James Murray. He also has a very beautiful book where he explained the theory behind. And one of the results that I think is interesting because it's really very mathematics can provide some answer. Here you have the tails also of animals. I don't know which animal they are. And here is the model. And you can see that you can never find a tails where the stripes of the spot are longitudinal. You can all have rings or spot, but never a tail like a line along the tail. So this is a mathematical proof. And indeed, I don't see any animals that are the tails with this longitudinal stripes. So this in some sense where mathematics meet realities, or is here biology. Okay, so one of the possible mechanisms is the one that Turing created in the 52 with this pioneer paper. And the idea is in some sense simple, but at the same time odd. The idea of the Turing was the following. So Turing studied the problem of morphogenesis, so the creation of shapes from embryo, animals, also human. And the idea was the following. So take two chemical reactant that reacts via some nonlinear function f and g that are so u and v are, if you want, the density of some chemicals at position x and y on the plane at time t. Okay, and so if you take only the reaction, after some times, the reaction converges to the equilibrium, is the thermodynamics. Okay, and so if U and V have some color, after some time in your dish plate or your tube, you will have a uniform color. Uniform, I mean spatial uniform. Okay. On the other hand, suppose there are no reaction for some reason, you only have diffusion. So you take, I don't know, a bottle of perfume here, you open, and the perfume go around in the room. But again, at some point, there will be a uniform amount of perfume everywhere in the room. Again, thermodynamics. So the idea of the Turing was the following. What happens if I put together the two mechanisms that isolated, they tend to uniformize the substance, that the density that are spreading, but I add two more ingredients. The first one is that one of the two, say V, should inhibit its own production, but also the production of U, while U should activate, so they promote the production, so you autocatalytic activator, if you want, because it produces itself and V. And moreover, you assume that one of the two, V, diffuse faster than the activator. So with this idea, what Turing proved is indeed that you can have a diffusion-driven instability. So starting from an homogeneous solution, which is of course a solution of both equations, because the Laplacian operator vanishes when you have a constant function, constant in time, constant in space, sorry. U and V are the solution of the reaction diffusion. So you have an homogeneous solution, which is a solution of this equation, but becomes unstable because of the diffusion. Okay, and so this is the idea. So this is a first order. So it can be studied in a linear way. But then once the instability is set up, then you have the growth of the solution from this initial condition, and then the nonlinearity that are hidden in F and G that will promote the creation of pattern. And so the idea is that with a very simple mechanism, Turing was able to propose a possible creation of shapes or morphogenesis from a simple embryo. Nowadays, the idea of Turing pattern goes well beyond this initial starting point of biology. And indeed, this is a natural physics of 15 years ago, more or less, where it is stated that the Turing mechanism is now a paradigm for the self-emergence. So every time, so not every time, sorry, very often, once you find this spontaneous emergence of some motif, then maybe behind this is the Turing mechanism that can explain this mechanism. Okay, so the idea today is to show how this Turing mechanism can be modeled using networks, and then we go on to higher order network like simplicial complexes and hypergraph. So I don't need to insist too much with you that networks are everywhere, networks are important. Here what is important for me, if you think again of two chemicals that should react, they should be nearby. Or if you think of animals, so prey-predator, they should be nearby to be in contact. And so one can imagine that in the space, even if the space is continuous, there's a reaction occurs locally, so they're localized in some patchy area, and then these chemicals or animals can only diffuse across some channels. And so this is very natural to imagine that you have a network behind this kind of mechanism, because you have reaction in the nodes and then diffusion across the link of the network. Okay, and so this is the idea, the idea of considering nodes small enough, so portion of space, but if you want, large enough to contain many chemicals of many animals, of many agents in general. And this is the idea that Robert May put to the fore in the 70s, studying the stability of ecosystem. This idea of metapopulation. So you have a node which is small, but large enough to contain many agents. In such a way, inside the node, there is no more space, and you can describe the evolution of your species just by a differential ordinary equation, not a partial differential equation. Okay, so once you have this, you replace the continuous space with a discrete one. So I is the node index, I go to 1 from n is the number of nodes that you have. And so because of this metapopulation assumption, the evolution of u and v and node I depends by some function f and g only on the density of u and node I and v and node I. There is no contribution from other nodes. Okay, so this is the simplest part, is just the local reaction. And this is the idea that Nakao and Mikhailov brought to the fore in this natural physics paper, again, 15 years ago, more or less. So now let me introduce the diffusion. To introduce the diffusion term, let me introduce the incidence matrix, BIE, that tells you if the node I is in the edge ij, and if it's the tail of the head of the link. And then if you define the vector u as the state vector, so each component tells you which is the amount of u in node I, and you define the vector occurrent key that each component, so you have as many components, as many links in your network, then you can use the Fick's law to say, okay, the quantity in the link E is given by the difference of the quantity in node I and j that at the end of the link, okay? If you use the matrix B, you can write in this way. Well, this is just the first Fick's law. And the second law is the continuity equation. So this is the Kirchhoff law, if you want. The evolution of u and node I without a reaction, only because of diffusion, is the sum of incoming and outgoing current at node I. So this is the divergence in some sense. This is the gradient, and this is the divergence. Okay. Oh, okay. And if you put together the two equations, you end up with the matrix BB transpose, which is nothing but the Laplacian. So the Laplace matrix of the network comes in a natural way once you use the first and the second fixed equation to describe diffusion across the link of the network. Let's observe that here in this way you obtain a first order with respect to t equation. So it's a parabolic equation that implies infinite speed of propagation. This is not physical. For the rest of the talk, I will do with this. But indeed, one can modify this equation by adding a derivative of chi with respect to t, and so end up with a second order equation for u, which is a sort of relativistic Turing pattern that we studied recently with a student of mine. Okay, but for the moment, for today, I will consider partial differential equation, first order differential equation. Okay, so putting all together, we have this idea that you still have activator inhibitor sitting on each node. They react in the node because of this equation, nonlinear terms, and then they diffuse via the links available in the network. Okay, as I already told you, the inhibitor diffuse much faster than activator. This is a condition, a mathematical condition that you can see once you derive the equation. And so the matrix L, so the Laplace matrix is symmetric because I'm assuming to have a undirected network, and the A is the adjacency matrix. Okay, so here is an example of a Turing pattern on a network. So just doesn't matter really which network is, and the system is the Brusselator. It's a nonlinear system. Okay, I'm from Brussels, so I use the Brusselator. You can do the sysnet you want. The dynamics is independent if you want from the model. But what is important here that normally, if your network is not has not some physical reason or is not embedded in some physical space, the fact that I put this node yellow in the center is just my choice. I could have put over there. Okay, so pattern here is not like a motif on the skin of animals, but it's just a distribution, heterogeneous distribution of densities on nodes. Okay, but of course there is a recent paper by Bogun and co-authors where the network is embedded in some hyperbolic space, and there is really a meaning of the location of points where you have high density, low density with respect to this embedding. So if you have an embedding in some space, patterns can really a meaning as pattern as in the skin of animals. Okay, I will briefly present you which is the idea behind the Turing bifurcation because I need in the following. So the idea is the following: you assume that there is an homogeneous solution, so space independent, so U hat and V hat, which is the solution. Let me go back. Of the reaction part. But because the Laplace matrix admits the vector 1, 1, 1 as eigenvector with the eigenvalues 0, once we evaluate this solution on U hat and V hat, also this part vanishes. Okay, and so the solution of the reactive part is also a solution of the whole system. This will be important at the end of my talk. Okay, so this is a solution for the whole system. You linearize because, as I told you, Turing instability is a first order instability. And so you end up with this matrix G tilde, which is nothing but a Jacobian of the system, where you can recognize the Jacobian of the reaction part plus the diffusion part. Okay, this is a huge matrix because it's two times the size of the system, because here is the size of your network. Okay, it's very huge. But then you want to prove that this matrix admit at least one eigenvalues with a positive real part, because you want to prove that if you have the U and the V positive, this system is unstable and you go away from the equilibrium U hat and V hat. Okay, so instead of studying the stability of very huge system, what one can do is the following: observe that the matrix is symmetric, so you admit an eigenbasis of eigenvector that are orthonormal, and moreover, you can the spectrum with the convention that I use is non-positive. This is 0, this is the largest one, and or the other negative. And then you have a new basis where you can decompose your perturbation, and you make down subs that this perturbation evolve in time thanks to these exponential growth terms. Okay, and so everything now is to prove that there is at least one alpha, so one eigenvector eigenvalue, such that this small lambda has a real part positive. In this way, it will be unstable. Okay, observe here that here we gain a lot because now we have a 2x2 system instead of 2n by 2m. So also from a algorithmic point of view, it's easier. And so the idea is the following: you compute the root of the system, the one with the largest real path color dispersion relation. Here you just plot as a function of, so this is a capital lambda is the spectrum of the Laplace matrix. These dots, and you can see that here in this case, indeed, I have some positive values, a lot of value of positive real lambda. Okay, and so in this case, you have a pattern. And so this is the example. So you plot here the relation dispersion. Here you have the system that is evolving on the network. And at some point, you will see that there are some nodes that will acquire a high number of large densities. They will be the nodes with the higher degree. Indeed, one can prove that nodes with the higher degree will have a higher amount of density. Here. It's the same plot. I'm sorry, this is not nodes, it's times. The same plot where I show you ui as a function of t with this stripe-like. Okay, so up to now the network were undirected. Now we can consider directed network, and this has been done by Malbor and Duccio, a collaborator, 10 years ago. So now we assume that L is an asymmetric matrix, but it's still diagonalizable. So we have still an eigenbasis, and now I take for L the matrix where here I put the in degree and not the out degree. Okay, so the spectrum is complex, but you can do almost the same computation as before. And now what you find is an inequality that defines a region of instability. So in the complex plane, you draw here, like in light blue, the region where this quantity is satisfied. S1, S2 are polynomial, or this is the fourth order and second order in the coefficient of the model. And then once you put your network, you draw the complex spectrum. If the spectrum falls inside this part, then you have a motif, Turing motif, while if it's in the white part, you don't have it. Okay, and now you can have a new kind of motif that are more like waves because on the imaginary part of the complex spectrum. Now you can have also a temporal evolution, not just a spatial one. And so they are called Turing wave or quasi waves. Okay, what we did recently with the studio of mine, Marie and Riccardo, is that indeed you don't need eigenvectors. You can have a directed Laplace matrix which is degenerated. So you have a generalized eigenvector, and you can prove the same. You can use the few eigenvalues, eigenvector that you have the same region as above. This now is green instead of blue. And if you have one eigenvalue that fall in this region, then you can have a patterns. Okay. And so here again, my network is much larger than this. It has, I think, 10 nodes, but you only have 4 eigenvalues. This is enough if you have 1 eigenvalues that provide instability. So you really don't need anymore the existence of a basis. Okay. So in conclusion, for the first part, you need the 2 diffusive species. The inhibitor will go faster. And as I say, you have this PDE because you have this infinite speed, but we can now read off all these quantities. So let me now go to the part where I go beyond network. I will very briefly skip past this part. One example of beyond network, where you have a network is composed by multi-layers. A multiplex network is composed in this example by 2 layers. Now you can have a species that move on 1 layer, on the second layer, but then can also cross across the 2 layers. Okay, and so here you have this parameter D12 U and V, which is the diffusivity across the 2 layers. One can write exactly the same equation as before. One can play with this parameter dV12, and you can prove that if it's 0 now, the 2 layers are decoupled, you don't have patterns. Here I show you the maximum of the relation dispersion is negative, and indeed, if I perturb my system, the solution go to the equilibrium. Okay, but if you increase dV12, at some point you pass the 0, and for instance for 1/2, you have a positive value, and indeed if you perturb the initial condition, the system now is divided into patterns. Okay, and so here the 2 lines are the first and second order approximation, and the dots are the real system. So we can also have a theory, analytical theory to explain this bifurcation. Another possibility is consider temporal networks, so networks that do evolve in time because the links are rewired, are moved, or because the weight of the links changing time. Here, one can do two different approaches. One approach where you say, okay, the network switch very fast with respect to the dynamics on the network. In this case, it's a very simple example where you have 6 nodes, and each time step, you only have 2 nodes that are connected, and then you iterate this in time. Okay? Of course, on each network, you can never have a Turing pattern because the nodes that are deconnected, they cannot interact, so they cannot exchange anything among them. But if you do this sum, in some sense, or this average of networks, and you can prove that at the end you have an object, you see well defined, then you can prove that if the final object has Turing pattern, if the switch is fast enough, then you can prove that also the initial system has Turing pattern. This is the average theorem of dynamical system. Okay, but we can do also, you can remove this fast assumption. You can have a generic Laplace matrix, symmetric in this case, that evolve in time with any function of time. But because this is symmetric, you still have an eigenbodies or eigenvector, which are orthonormal for all t. And then you can write the time evolution of the eigenbasis projected on the same eigenbasis. So you linearize, and you obtain once again the same equation as previously, where the Jacobian of the reaction plus the part due to the Laplace. But now you have this extra term that mix all the contribution, because now the evolution of the mode beta depends on all the other modes. So this is sometimes a new relation dispersion, which is a bit more complicated. But anyway, I show just an example, a very simple network where you have 3 nodes, whose links evolve in time according to this cosine-like function, and there is only parameter omega. If omega is 0, the network is static. If omega is not 0, that the links evolve in time is one example of evolving link. One can prove in this case that for the static network is more easier to have Turing pattern. So let me explain. Here again, I use the Bruce-Slater model that depends on 2 parameters. So this is in the plane BC, is the bifurcation domain. White, no pattern, black pattern. So the first row is for the static network. Indeed, you can see that if you take these 2 points, each one gives you pattern. So a solution that is not homogeneous in space. While if now you switch on omega, omega is equal to 2, you see that the exact same point here that was previously in the black now is in the white. And indeed, it now converges to the equilibrium, while previously you have a pattern. Okay? And here, moreover, you have this oscillating pattern, because in some sense it feels the fact that the network is oscillating. So this is an example where the network can oscillate with any speed, have a very slow, because omega can be small, but then you reduce the possibility to have a Turing pattern. Okay, now let me pass to the second part, which is the part on beyond network. So again, I do not have to explain you that a triangle empty is not the same thing that a filled triangle. So this is very well-known people in this audience, and also the 2 possible ways of modeling this I order, that is simplicial complexes of hypergraph. So I will start first with hypergraph, and then we'll pass with simplicial complexes to present some results that Ginestra present Monday afternoon. Yes. Okay, so hypergraph, just to fix the notation, hypergraph is just a bunch of nodes that are grouped together in hyperedges, this kind of set, and each node in the set can be exchanged without any preference direction. Okay, and so you can build the adjacency matrix or the hyperedge matrix by using again the incidence matrix E that I devote B in the previous slide. Okay, so here what one can do, this is a very simple example that I will need in the following, is that you can use a sort of mean field on each hyperedge. So because I say that the 2 nodes here can be exchanged, if I'm interested in the influence on node I can say, okay, they can be exchanged, and then what doesn't matter is the size of the hyperedge. So this is a very simple way of saying this. You say that I can introduce an equivalent network, because now I have a weighted network, where the connection between I and J is one of those 2, depends on the size, C alpha alpha, of the hyperedge times some power, that can be positive or negative, to influence in some way the nonlinearity of the system. Okay, so this is a possibility, and this has been, sorry. I have, okay. It doesn't work anymore. Okay, and so this has been done again with Duccio, and we proved that one can have indeed patterns by using this mean field assumption on each hyperedge. But one can fully exploit the structure of the hypergraph by using the adjacency tensor A. This now depends on d+1 indices. In this case, the tensor is symmetric because, again, I can exchange all the nodes in each hyperedge, and this will not change the distribution. Okay, so you end up with a system, with the equation. So I'm not interested in the equation per se, but then again, you assume there is a solution, U star, V star of the reaction part, and then you perturb around the solution, so you linearize. And if you consider only hyperedge up to size 3, this is so p equal to 2, then you end up with this equation, which is again is very similar to the previous one, but now we have two terms, the Laplace of the pairwise interaction and the Laplace matrix for the link-link interaction in some sense. And also you have now the Jacobian of the coupling H1, so the coupling which is given to the links, to the nodes node, and the coupling because of the links, okay? So in general, you cannot go any further with this equation because the matrices L1, L2 do not commute, so they cannot be simultaneously diagonalized, or the matrices JH1 and JH2, they are not in common, okay? But under some assumption of L, say on the topology, on the coupling, you can go on and you can produce a theory again, as we did before with the relation dispersion, okay? Alors, now I will really give you two slides about a recent project that I'm doing with some student of mine. We already spoke or heard about directed hypergraph, and here a few examples of directed hyperedges. This is a three hyperedge where you, sorry, a two hyperedge where 3 nodes, 2 and 3 influence one but do not influence each other. Here you have the 3 that influence 1 and 2, and 1 and 2 influence each other, or you have higher combination. So you have 4, so 2, 3, 4 that are against 1. Here you have 3 and 4 that are against 2 and 1. And here you have 4 that is against 1, 2, and 3. So you can have all the combination of this kind of direction. So I put the arrows just to mention this direction of the reaction, but there are no links. There are really hyperedges here. Okay, and so you can, you can encode with this kind of tensor where now you have two indices, the one for the size and one for the directionality. If you want, you can call head the number of points where you point to, and tails the other. And because 2 and 3 can be exchanged, I can put here any permutation of 2 and 3. Okay, or here again, sorry, it is a 1 and 2. You can permutate 1 and 2, and permutate 3 and 4 because each one are separated. And so if you do this, in general, you have this kind of adjacency tensor, where D is the dimension, M is the number of nodes in the head, so where towards the system point to, and Q, which is the sum is given by M plus Q is equal to D plus 1, so the dimension, is the number of nodes in the tail of the hyperedge, okay? So here we have a Q species that promote the evolution of M species, but they do not interact each other, while the M species in the head, they can interact each other. And so if you write down the equation where you have this vector xi that describe the amount of species and node I, then you have again the isolated system, so the local reaction, and then you have a sum of terms that depends again on the size of the hyperedge and the directionality. So you can play on both, on the dimension and on the number of nodes in the head. Okay, so here to simplify, I will not put any more the permutation. This is clear from the context. Okay, so in this form is too much general because this is a function G that depends on too many variables. So one thing that can be done is often been done. Assume that G of diffuse-like shape. This means that once you evaluate this on the homogeneous solution, this function vanishes because it's 2 times the same function evaluated in the same point with a minus. And so this is a very simple assumption that helps you to say that the solution that was the solution on each node is also the solution on the whole system. Of course, you can assume that this function G vanish when all the components are the same. This is a non-invasive assumption, but at the end, it's the same result. Okay. Once you do this, you can again linearize about the equilibrium solution, and you end up with two matrices that, to the best of my knowledge, as the first time that I saw this kind of matrices for directed hypergraph, which is one part is symmetric, which is once the two nodes are in the tail, in the head. Okay, because once you linearize the previous equation here, you have to linearize this function, now this one, so you have to take derivative on this part and also on this part. But so the node I is always on the head because it's the node that you're interested in. Well, once you linearize this part, you can have derivative with respect to the first group of nodes that are in the head, but also with respect to the second part of nodes that are in the tails. So this gives you two different matrices that are the matrices that are here, where the matrix health, as I call, is when I and S are both in the head of the hypergraph, hyper edge here, and so it's just a sum of the contribution from all the possible way these two nodes are in the all possible head. While there is an asymmetric part, which is this L check, where it's now I is in the head, while S is in the tail. So this is, I think, the first time that this kind of two matrices has been put to the fore. And what I can do again is to study the emergence of Turing pattern on directed hypergraphs. Here, just to show you a simple example, I took this ring-like structure. This is the undirected case. So here, all the nodes can interact with each other. And indeed, the spectrum is real. So the Laplace matrix is only one matrix, which is the symmetric one. So it's real. These are the region that I showed you previously, where you can, if you fall down, you have a Turing pattern. And indeed, the black point do not touch this green part. And so you don't have patterns. Everything goes to equilibrium. While if you now increase directionality, so here I have two nodes point to one node each time. And this is the spectrum of the hypergraph. Of course, the result are for a much larger hyperring than this. This is just to show you the example. I think here there are 15 hyperedges. Okay, and so this is the spectrum of this hypergraph. And then again, it doesn't touch the green zone, so you don't have pattern because everything goes to equilibrium. While if I put now one node that point to, so one node that point towards two nodes, so there are two nodes in the head, then now the spectrum is like this, and now you have several points of the spectrum that fall in the green zone, and then indeed once you do the simulation, you find pattern. So in this simple example, you can show that increasing the directionality increases the chance, if you want, to have Turing pattern. So in the symmetric case, you don't have anything. You put a bit of directionality, you still don't have anything. But if you put enough directionality, you can have patterns. Okay. Okay. So this is just a summary of this example, where again, the plane B and C, I put, so you have to assume that the green is also behind the yellow and the orange is also behind the yellow. So the black lines is the symmetric case. So there are all the parameters B and C for which I have Turing pattern on the symmetric case. The yellow is one you have Turing pattern for the 1, 2, and 3 directed. The orange where you have only for 2 and 3 directed, and the green for the 3 directed. Okay, so you have to think that the green is also behind. So this region is much larger for the green part than for the yellow and for the symmetric case. So this shows you that the previous picture was not just a chance, but it's the large number of parameters B and C for which you have this phenomenon. Okay, so let me now pass to simplicial complexes. I don't know how much time do I have. Okay, so okay. I check in the literature, there is a paper which is titled is Turing pattern in simplicial complexes, and but looking carefully to the paper, I don't think the authors fully exploited the structure of simplicial complexes for two reasons. First of all, is a still node-centric point of view. So you have a simplicial complex, but where the species are again on the nodes. Okay. And on the other hand, they use a single huge incidence matrix that at the end comes out with a network, a projection on a network where the links of the network are again related to the size of the triangle or the tetrahedron and so on. So this is a paper where indeed there is Turing pattern, or the theory of Turing pattern, simplicial complexes, but for me, it's not really fully exploited the idea of simplicial complexes. So I will try to show you what is possible to do in this case. The idea is that this is the picture that also Ginestra already showed you, that if you have a spatial complex, okay, there are nodes, so you can have signals or nodes, but you also have links and triangles and higher order structure. And so you can think to have some variables that evolve on the links, like a current, or some variable that is attached to the triangle, some fluxes, some current, okay? So the idea is it possible to couple these different structure and see if you have, again, Turing pattern on spatial complexes, but really using nodes, links, and triangle, and so on. And so, okay, I skip this part because you already know how to encode a spatial complex by using the matrix B. Also, you will need this Hodge Laplace matrix, but you already saw what this kind of matrix is. And so the idea is the following. Now you can write a simple model where you have only two species, U that lives on nodes. So this is the node species that for the moment is just a one-dimensional species, only one number. And then you have V, which is the species that lives on link. And again, you think that V is just one number, okay, is the density. So this is the reaction part. This means that, so this is a vector, so you should read this component Y. The evolution of U on some node I is given by F in node I times B1V. So again, this is the divergence of all the incoming links with some quantity V in node I. And then here you have the interaction among the nodes because of the Laplace matrix, the node Laplace matrix, so the network one. Here you want to know the evolution in time of the V on some link. So again, you look at this equation component Y. And so this depends on the quantity V on the link, of course, but also on the gradient, so the nodes U that are at the border of the link V that you're interested. And this can be done with the transpose matrix B. And then now you have, instead of the plus L0, because you have L1, because you want to know how links interact by touching different nodes. In this case, I don't have triangles, because otherwise you could have also the fact that links interact via triangles, okay? And so, as in the case of Turing pattern, you have to assume the existence of a solution homogeneous in space, so the same solution for all nodes, for all links, that I call U star and V star, that should solve this equation, okay? So observe that you can write U star and V star as a scalar times the vector 1, 1, 1. And so if you remember what I told you before, you want that this solution, U star and V star, is also a solution of this system. So you plug in, and then you end up with these two equations. You have to solve, you have to prove that L0 U star is 0, but also L1 V star is 0. The first one is straightforward, is the same for the network. But the second one is not always true. It depends on the spatial complex. And indeed, to solve these two equations, you have to solve those two equations for the matrices B transpose. And this is exactly the condition that we found with Ginestra in related by different framework, which is the synchronization of topological signals, where again, we show that not every simplex can sustain a synchronization, global synchronization. It's the same here. Not every simplex can sustain Turing pattern. There is really a constraint which is related to how the links and the triangles are matched together. In this case, this condition is simply that each node should have an even number of links incoming or outgoing. Okay, if you add triangle, the condition is more complicated. With Ginestra, we were able to construct a few examples. One is a torus, where you have a triangularization of the torus, or you have what is called a waffle, which is a strange structure where you have pyramids glued together in donut way, if you want. But let me observe that if instead of spatial complexes, you use a cell complex, so where you replace triangle by square, this condition is also satisfied. So in this case, cell complexes are more easy or more so easy to use for synchronization and for Turing pattern that spatial complexes. Okay, Ginestra also presented this this work on models. Let me give him a bit more information. So in the previous one, I put together the interaction between nodes via the Laplace matrix, the interaction between links via Laplace matrix for the links, okay? Because with the Laplace matrix, only structure with the same dimension can speak. But one can be interested in say, okay, I would like also to know how the interaction of the links directly act on the nodes, or how the interaction of the nodes directly act on the links, okay? And so this is given by the Dirac matrix, that in the case of a network, I only have these two matrices, while if I would have also triangles, I would also have the B2 somewhere, okay? And so here what we prove with Ginesta in a recent paper, that you can have patterns also once you remove the Laplace interaction. So only Dirac interaction is enough to promote the emergence of Turing pattern in this case of system. So here's an example, again, because the condition, the constraint that I showed before, that B1 should have 1, 1, 1 as an eigenvector, and B1 transpose the same. This is an example where you have a very simple network, if you want a cell complex, where each node are degree 2 or 4 and have a number. Okay, and this way you can prove that you can support Turing pattern. And indeed, if you do the simulation, you can find pattern. What is important here is that in both cases, U and V are inhibitor. So this is not possible in networks. So if you remember the first few slides, Turing idea is that, okay, I need two diffusing space, but I should have one inhibitor and one activator. Here, this is no longer necessary. The Dirac interaction is enough to have inhibitor-inhibitor pattern, which is a really new result that we found recently. The last point is, again, Ginesta briefly showed this on Monday, is the idea that, okay, up to now I have one species on the node, one species on the links. But this is not a restriction. You can have, for instance, two species on the node, one species on the link, or vice versa, two species on the links and one on the node, or any other combination, okay? The only point, so here my vector key has two components, the two variables on the node, and the psi as one component, which is the current on the link. So the only point is that now once you project from the node to the link or back from the link to the node, you have to change the dimension because it's no longer one-dimensional object. And then you need this metric function that in the simplest case now you took the identity matrix times some constant. And so you have this modified, if you want, the three-way Dirac operator, where now you have the Dirac operator, but that now takes into account that you have a different dimension in the links on the nodes. And indeed, if you do, so you write almost a generic model where you put some parameters. So this, again, it's not important the model per se. But what you can prove, again, here is in the plane sigma 1, sigma 2, that are the two parameters controlling the dynamics on the node. Then you can have Dirac and Laplace pattern. So once this coefficient C2 is not 0, or you can have a pattern only with Dirac. So when C2 is 0, you remove the contribution from the Laplace matrix, okay? And there is some differences. So in the white zone, the homogeneous equilibrium is unstable, so you cannot have a Turing pattern. Here you have three zones where in this yellow part, the equilibrium homogeneous remains stable also when you have a diffusion. So here you don't have patterns. While here you have a stationary Turing pattern, and here you have waves, if you want, waves like. In the case of Dirac, we lose this part, the stationary one. And so in some sense, it's easier to have a Turing pattern because once you have parameters in this region, here you converge to the equilibrium, while here you converge or to stationary pattern or to waves. Okay? And also the shape of the patterns is a bit different. This is my last slide. So if you took the same parameter, sigma 1 and sigma 2, in the case of Dirac Laplace, this is the kind of waves that you obtain. So this is the U variable on the links. This is the V variable on the links, on the nodes. And this is the W variable on the links. And these are the kind of waves that you obtain because here you have this dynamical pattern. While if you take exactly the same value, but you set C2 equal to 0, so in some sense you only have Dirac, they are much more regular. So you can see that, okay, maybe you cannot see very well, but there are, phase of position is a bunch of nodes in the first, so for the variable U, another bunch of nodes for the variable V, and the same for the links. So this is the case of two torus, so this is a cell complex again, and this in some sense reflects the two directions of the torus, if you want. So the longitudinal one and the latitudinal one, okay? Where you can have nodes seen in one direction that are in some phase, and node that in that direction in the opposite phase, and vice versa for the links. Okay, I think that that's all. Thank you very much for attention.
Thank you. Any questions for the speaker?
interesting, but in general, when I look at this Turing pattern analysis, I find the mathematics always a little incomplete because you just show typically that the constant pattern becomes unstable if you add diffusion, but you don't show what the stable patterns are, what their properties and characteristics are.
Yeah.
And now here in particular, then if you look at the tails of the leopard or the jaguar, so one doesn't really show that you get spatially, temporally, asymptotically temporal constant patterns. So you don't show that that the tail is not flickering. I mean, typically we would have a Turing pattern which is a spatial temporal pattern, and then it would change all the time. But that is, of course, not what is happening with the tail. Yeah. And here, in your case, do you really get fundamentally different types of behavior than what you get with the ordinary Turing pattern? And can you characterize or identify those behaviors?
Okay. Yeah, no, it's true that, so this is a linear analysis. This is a linear analysis of Turing part. So you just know that is a bifurcation. And in principle, if there exists another homogeneous equilibrium, your system can go with another equilibrium homogeneous, of course. Yeah, it has to go somewhere. Okay. I completely agree. Now what one can see, not really, so one can prove that close to the bifurcation, if you have only one eigenmode or two eigenmodes that are unstable, then the pattern for short time close to the bifurcation align on these eigenvectors. Okay, so this can be proved. But what happens very often is that the same distribution stay longer. So in some sense, you can predict. So the example that I show you where you don't have an eigenvector, but you have a generalized eigenvector, it was some sense a surprise for us to see that using the generalized eigenvector, so the unstable one, you can predict the shape of the pattern even for a long time. We don't have a proof, but it seems to be true. So it seems that once you are close to the bifurcation, you follow this eigen direction, and you remain there for a long time. No, I cannot prove it. No, I say that is a numerical evidence, and no. And moreover, there is okay, the system is deterministic, but initial conditions are random, close enough, because again, it's a linear stability. So I don't know how much close enough should be, but suppose there is some sense close enough. But if you do 2 times the same simulation, because the initial conditions are random, you don't know if for some reason you took another direction and you end up with another patterns. Yeah.
How many different patterns can you get?
I think you can have a distribution of patterns. I agree with you. But this is an open question, I think, also in the framework of continuous Turing pattern.
Any other question?
Yeah. Thank you, Timoteo. Very nice talk. I was wondering, at the very beginning, you used the Brusselator, which is a variable to species model. And at the end, you are using a 3-species model, right?
Yeah.
What happens with the 3-species model in the previous works? I mean, they play a role, the dimensionality here, to say that the model is independent. I think this.
Okay, so Turing patterns are normally studied with 2-dimensional system. This is the reason, I think, because Turing did in the origin, but there is no reason for that. You can use any dimension. What you can prove that if you have only 2 species, on, say, on the flat surface or on the symmetric network, you cannot have waves. To have waves, you need or 3 species or a directionality induced by the network. Okay, so yeah, there's a difference between the dimensionality. But otherwise, I think that if I take the last system with 3 species, instead of a simplicial complex I put on the network, I think one have, so maybe the pattern will be more like that one. And because yes, the really Dirac operator, they play an important role, but I don't think there will be so much difference, but in this framework here. Where you still?
I think you can go from n larger than 2 in the complex Gibson-Landau framework, and it works.
Yeah, see, I didn't show here the Gibson-Landau, but yes, you can do. We use the Stewart-Landau for the synchronization because it's, but yeah. So in principle, this can be done in any dimension. You can use the Rossler or the Lorentz model that 3-dimensional. You still have Turing patterns.
You have this directed hypergraphs. I'm wondering what is the rationale behind it? Why you want to define that way? Is there any existing book people use this kind of idea?
Okay, so Jürgen, Raffaella, Christian, they have some result about directed or oriented hypergraph. You can show on Monday, so this is the definition. But what I didn't find in the literature, but please tell me if I'm wrong, is the existence of those two matrices. In all example that I saw, okay, if you just orient like in the chemical hypergraph, this orientation is just a label as in the spatial complex. You orient them, you don't dirige them. They're just orientation. So if you orient them, they remain symmetrical one. But there are some papers where they say asymmetric or directed hypergraph, but I never find this asymmetric Laplace matrix. The Laplace matrix is in the paper are always the symmetrical one. So I think this is really the key to have this directionality, because the spectrum of this matrix is now complex, while the spectrum of this one is real. But if you sum up, this is the one that wins. So at the end, you will have a complex spectrum.
You already come up with such an asymmetric.
Yeah, in the graph, yes, I agree.
For hypergraphs, that's the fact is that in input and output nodes, you have several nodes which you can permute.
Yeah, I completely agree. I don't say that I discover anything new, but I never see in the literature explicit these two matrices.
Directed graphs.
Yeah, right.
Yeah, of course, the directed graph. Yeah, the network. Yeah, sorry.
Any other question? If not, I propose we thank the speaker again.
Thank you very much.